Okay, so for quiz 3, we're going to start with questions 5 through 14. They give you this pictorial, display demonstration of what we're doing. We're doing hypothesis tests. We have the null hypothesis and the alternate hypothesis. Somewhere earlier in the question, back on question 1, it states what the null and alternate hypotheses are. So we're talking about the mean value being no bigger than 200. That was in the null hypothesis against the alternative that mu is bigger than 200. With that in mind, well, we know that less than 200 is the left curve, and therefore greater than 200 is the right curve. So with that in mind, we've already answered number 5, that the left curve is that associated with the null hypothesis. Naturally, curve 2 would therefore then be that which is associated with the alternate hypothesis, some different mean value. Number 7 asks, what is area 1? Area 1 is, I'll kind of tell you what these are. These are on my cheat sheet that you have, or some of you already have it because you've been watching the final exam practice sessions. The area under the null, under HO, and inside the rejection region is a type 1 error. Area under HA and outside the RR is a type 2 error. And then area under HA and inside RR is power. Okay. What constitutes the rejection region here? Well, as a reminder, this type of test is a right-tailed test. How do I know it's a right-tailed test? You can look at the alternate hypothesis and see that it's a greater than symbol. So that means this is a right-tailed test. And because it's a right-tailed test, the form of our rejection region is something like RR colon X bar greater than CV. It's a right-tailed test, so it's a right-tailed rejection region. So for question 7, we want to know what this red area is here. What is this red area? This is everything that is under which curve? Is this under the null or under the alternate? A lot of people think that it's under the null, but notice that the red shaded area is hugging the pink curve, and so it's under the alternate, and it is outside the rejection region. Notice that the rejection region says in order for you to be inside the rejection region, you want to be on the right side. This greater than symbol indicates that everything to the right is the rejection region. So with that in mind, this red shaded area is outside the rejection region. So this must be a type 2 error, or the probability of a type 2 error. What is area 2? Area 2 is everything under, this is underneath the null hypothesis curve now. This is the green area. Question is, what is this green area? This is underneath the null hypothesis curve, and this time it's inside the rejection region. Again, because the rejection region is a greater than symbol, it's to the right. Everything to the right of the critical value is inside the rejection region. So this is under the null hypothesis and inside the rejection region. So number 8 is a probability of a type 1 error. And then she says in question 9, what is area 3? Area 3 is everything on the left-hand side. We don't really actually have something for this, so I'll just say this. I have to type it. This is not on my cheat sheet, so this is a new. Area under the null and outside the RR is correct rejection of the, or correct acceptance of the null. This one I do not have on my cheat sheet. You might want to add this as your own, but area under the null hypothesis and outside the rejection region is correct acceptance of the null. So with that in mind, we can go ahead and answer number 9, which would be probability of correctly accepting the null hypothesis. I'll just label that as B, because that's the answer choice for that one, according to the PDF. Number 10, what is area 4? Complement of area 1. Complement of area 1, area 3, which we can't really see, sorry, area 4, which is the complement of area 1 to the right of the critical value. You can't really see it because she hasn't shaded it, but if she were to shade it, she would have shaded it like this. Let's get this tool out. This is what we're talking about. The reason she doesn't shade it is because it obviously overlaps the green area that we've already drawn there, so she doesn't draw it because then it would kind of like steal the spotlight from the green area. We're talking about everything to the right of the critical value that's inside the rejection region and underneath the alternate hypothesis, underneath the HA, and inside the rejection region is power. So that would be your answer to 10. Now we're on to number 11. What is half line 1? Here's what always happens. So we're going to end up with 2 lines here. One of them is this guy. And another one is this guy, the critical value. So one dividing line goes to the peak of the null, and one dividing line goes to the critical value, okay? Here's how this works. You're going to put a bracket on this and an arrow to the right. You're going to put a parentheses on this and an arrow to the right. This is H null is true. And over here, on the other side is HA is true. Let's put some space here, okay? So that tells you the answer to number 9, or see, 11. Number 11 says, what is half line 1? Half line 1 is H null is true, or values of mu in H null. So you could say this is values of mu in H null, okay? I call it H null is true, but it's values of null that are, values of mu that are in H null. Conversely, they want half line 2, okay? Half line 2. I don't know why she did it in this order, but she did. So we've got a dividing line here, which is this guy and this guy here. This is accept H null. And as you probably guessed, this guy over here is reject H null. So half line 1 is the null hypothesis is true, basically values of mu that are under the null hypothesis. That would be mu in H null. 12 is, what does this guy represent? Well, this guy is just accept the null hypothesis, accept H null, and then 13 and 14. 13 says, what's open interval 1? Open interval 1 is this guy, which should be HA is true, or basically values of mu that are in the alternate hypothesis. And lastly, what is open interval 2? Open interval 2 is reject the null hypothesis, so the rejection region. Okay, that is what I'm going to discuss when I do part 3. This is one of the many things I'll discuss when I do part 3 of the final exam practice sessions. But this is a big one. This almost always shows up on the final. I'll say this: it has always shown up on the final exam for the past 5 years, to the point where if you were to take this test in person, you would have to draw this picture. But of course, we can't take. There's no taking this test in person. There is just her giving you a picture and then you assigning the correct variables and things and names to the shaded region, the half line, the interval, the curve, et cetera, et cetera. So that's how you do the set of the set of 10 questions that are here every single time. Cool. All right, let's clear all this. Let's jump down back up to question 1. Question 1 wants to know, what sampling distribution is the basis for the hypothesis is? So we've done this a few times now. We're going to skim the problem for some important information. Was it told to us that daily output levels for this production process were approximately normal? Yes, it's the last sentence of the first paragraph says, assume that daily output levels are approximately normal distributed. So we've got, yes, approximately normal. And then the follow-up question is, do we know the population standard deviation? Assume that daily output levels are approximately normally distributed with a standard deviation of 18 units. That is not the sample, that is the known population. So we are told that the population standard deviation is 18 units or whatever. That means AKA we know the population standard deviation. According to the tree, I'm not going to draw it because I've drawn it. If you haven't seen it yet, watch some of the old videos. But the tree, first question is it approximately normal? We'll say normal question mark. The answer is yes, so we go up to this branch. What is this question? This question says, do we know the population standard deviation? Is sigma known? The answer to this one is also yes. And because this is yes, we're going to be using the z distribution. The Z distribution is that answer choice that is associated with answer choice A. It even says random sample from a normal population, known variance. So number 1 is A. Number 2 wants to know the maximum value of a max probability of type 1 error. This means, this is interesting because this time we have been given a critical value. So up until now, I'll say this, up until now, we have always found the critical value based on a given value of alpha. This problem is asking you to find the value of alpha given the critical value. So it's kind of a flip of what we're accustomed to. Usually we find a critical value based on the value of alpha that they give us. This time we're trying to find the value of alpha based on the critical value given to us. How do I do that? Well, we have a distribution, so some sort of bell curve. We're told the mean for this process is 200 units. And according to question 2, what does question 2 say about the critical value? What critical value are they going to use for in question 2? What was stated about the critical value they're going to use?
203.
203. So I'll put that over here. And the probability of type 1 error is so type 1 error, just in case we didn't know, type 1 error is rejecting H null if the null is true. So this is why it's an error. We shouldn't reject the null if the null is true, but we may inadvertently end up rejecting it even though it's true. How likely will we end up rejecting it? So, well, when do we reject? When do we reject the null? When X bar is in the RR. And how often does that happen? Well, that happens as often as this number, as X bar is at this number or beyond. So we just need to find this area. So we're going to shade this guy here. Our goal is to find this area. Okay, so we want to know what's the probability. You can do this in a really long, convoluted way. I'm going to actually type this. What's the probability of type 1 error? That's being X in RR given H null is true, which is to say P is that X bar is greater than 203 given mu equals 200, which is to say now we're at a point where these are all equivalent, by the way. So you can say equals, equals, equals. We're going to continue with the equals. What have I told you about normal distribution probabilities that have X bar or X in them? What are our job is to do what? Convert these to what? I'm going to wait till someone says it. Our job about giving probability about random variables involving normal distribution. What is our job here? What's our goal with this sort of probability? What do we always have to, what do we have to do for exam 2?
Z-scores?
Yes, we have to convert that to a z-score. So our job is to convert this to a z-score. That means we need to use, I'm going to write this formula over here. X bar minus mu over sigma over square root of n. In our case, we have 203. That's the special value we have here. 203 minus what's our mu? That value is 200 divided by standard deviation of 18 over square root of what was our sample size. They told us back in question 2 that it's 81. So we get 3 over 18 over 9. That's 2. This comes out to be 1.5. And being in the rejection region means being in all this area to the right of this. So if I want to find the right tail area of a normal distribution, everything right of z-score of 1.5, what might I do? I'm trying to figure out the probability. Let's go back and say z greater than 1.5. Now we do normal CDF. Our lower bound is 1.5. What upper bound do we use? Well, we want to go as high as we can, so we'll just say 100 or 1,000, and we'll leave it at that. Lower bound 1.5, upper bound 1,000. And of course, we always leave the mean as 0. We always leave the standard deviation as 1. Okay? When we get this, we do normal CDF 1.5 to 1,000. I have my calculator today. Normal CDF 1.5 comma 1,000, we get 0.0668. It helps to go through that when you're being asked to find a type 1 error or type 2 error probability. It helps to start by saying what a type 1 error is. It's being in the rejection region if H null is true. Vice versa, a type 2 error is being outside the rejection region if H null was false, or HA was true, you could say. And then we say probability X bar greater than 203, convert it to a numerical thing. Okay, step 2 is done. Now we're on to question 3. What's probably a type 2 error if the mean was 205? Okay, this is going to change this wording a little bit. So we want probably a type 2 error, like I said, that would, instead of being the inside the RR, that'd be outside RR, assuming the null was false. And again, we want to be outside the RR, so how should I change this X bar? Well, if being inside the rejection region was such that X bar was greater than 203, obviously being outside the rejection region just means we need to change the greater sign to a less than sign. And what was our value of mu here? We're not using 200 anymore. They said assume that the population mu was actually not 200, but what?
$205.
Yep, 205. So we'll use that instead. We're going to recalculate the z-score for that. This will be 203 minus 205 over 18 over square root of 81. And this comes out to be -2 over 2, which is -1. This time, I'm trying to figure out being outside the rejection region, so that means I want to be less than that z-score of -1. So my normal CDF will look a little bit different. I'll say -1,000 up to -1, and this will be something like 0.1587. Let me double check that. Yeah, good. Any questions on this? That was number 3. So this is number 3 now. I forgot what number 2 was, but it was there moments ago, so feel free to go back to it.
This may be like a stupid question, but where did you get a -1,000?
What do I usually use for my lower bound when I do some sort of normal CDF?
It's a really large number.
Right.
But
Like,
isn't that a really small number?
what's that? So let's say I want you to find, here's a bell curve. Here's a z-score of -1.2. And I want you to find this area. What are you going to run in your calculator to find this area? If this is a z-score. So first off, what function always gives you the area underneath this normal curve?
Normal CDF.
Normal CDF. And I want everything between what two values? Or at least, what's very obviously my upper bound?
-1.2.
And what's my lower bound?
Negative infinity.
Yep. So what do I use as my lower bound? Can I plug in negative infinity here?
No.
So what can I?
Any big negative number. Okay, I get
Yep.
it now. Thank you.
Okay. That's why I use 1,000 for the other one, right? Because here, I want to go as far to right as possible, so I use positive 1,000 for that guy. Okay.
I have a question.
Sure, shoot.
Sorry.
Go for it.
Is that standard that when you're looking for type 2 errors, the lower is going to be like -1,000?
No.
Nope. Okay.
Well, here's why. Why did I, what was the null hypothesis for this particular question, Evelyn? Mu was what?
200.
Equal to 200 or something different? Because I don't think it was equal. It was something a little more specific.
Oh, 203.
Nope. Sorry, I think the null hypothesis was stated to be what? Test what null hypothesis? A manager wants to test the null hypothesis that, otherwise that was the alternate. A manager, read the whole sentence, be careful. A manager wants to test the null hypothesis that the new layout, what? The mean daily output is?
Oh, no greater than 200.
No greater than 200. As compared with the alternate, which says mu is what?
Greater than 200.
Right. So with that in mind, our rejection region will be of the form, because this is a right-tailed test. We talked about this when I had the drawing up there before. This is a right-tailed test. Our rejection region will be of the form RR equals X bar greater than some critical value, close squiggly bracket, right? Well, guess what?
Right.
If I swap everything, if this is a greater than or equal to, and this is a less than, this is no longer a right-tailed test. It's a left-tailed test, right?
Okay, got it.
Which means our rejection region inequality flips, which means that being a type 1 error is then being less than the critical value, and a type 2 error is being greater than the critical value, and all the inequalities get flipped. So generally speaking, no, to answer your question, no, it's not always less than for a type 2 error and greater than for a type 1 error. It depends on what the original hypotheses were. In our case, the original hypotheses were mu was less than or equal to 200 for the null, and then greater than 200 for the alternative. But if you change the statement of those hypotheses, you change whether we're doing left or right when we do our rejection region, right?
Okay, thank you.
Okay, going now on to number 4. Calculate the power of the test if the population mean is 203. The nice thing is sometimes we say probability of type 1 error is called alpha, which is also called the significance level. So this is alpha. Probability of a type 2 error. If you had to guess, if a type 2 error is called alpha, guess what the type 1 error is called alpha, guess what a type 2 error is called?
Beta.
Beta, good. And power just so happens to be 1 minus beta. This kind of makes sense because we talked about this even way back in the drawing where we had, if you recall, I had the critical value here, and I called this guy type 2 error. And then I called everything over here. Let's do a different shading. Let's do green. I called this guy power, right? Well, guess what? This chunk plus this chunk, these two pieces together add up to be how much? Well, there's all the area under the curve, so they adds up to be how much?
1.
1. So if I know that the total area under the curve is 1, and I happen to know the probability of a type 2 error, then I just subtract that from 1 to get power. So since our answer to number 3 was 0.1587, then our power is necessarily 0.8413. Any questions on that? Okay, I'm going to clear all this, or actually, let's not clear it just yet until I get to question 15. Calculate the probability that H null will be rejected if the population mean is 198, and then continue using a critical value of 203. We're going to, once again, say, what's the probability that X bar, if we do what, reject or, did you say reject? Yes, reject. What's the probability of rejection if population mean is 198? I believe that's what question 15 is saying. What's the probability you reject if the population means 198? So we're going to again say, what's the form of our rejection region? Is it greater than 203 or less than 203? Well, our critical value set was 203, and because this is a right-tailed test, we're going to say X bar greater than 203, because again, we're talking about rejection. We only reject if it's greater than our critical value. This time, we're assuming mu isn't 205 or 203 or 200, it's 198. So we recalculate a new z-score. So again, this part always gets kind of tedious because we have to keep calculating z-scores. Once again, z equals X bar, which is 203 minus mu. This time we're assuming mu is 198. In a previous part, we assumed mu was what value?
205 and then before that 200.
Yeah, exactly. Before that, we said 200. So just keep in mind that all that's changing here from problem to problem to problem when we're calculating what is called the probability rejection curve or the power rejection curve or something like that, is that we're going to be changing the value of mu. We're going to keep using the z-score, or not the z-score, but the X bar value, the critical value of 203, but changing the value of mu from problem to problem to problem. So we have 18 over square root of 81. This gives me -5 over 2, so -2.5. So that's going to change this to, oh, not -2.5, sorry. Just 2.5, it's a positive 2.5. And we need to make this to greater than 2.5. Use normal CDF 2.5 comma 1,000, which gives me 0.0062. I'm going to need to remember these values, so 0.0062. Got to remember this guy. And then we got to do it one more time for 207. So I'm just going to do one small thing. What if I were to change this value from 198 to 207? Then this would be -4 divided by 2, so it'd be -2. So change this. 207, 207, -2, -2, normal CDF, -2, comma, 100, I get 0.9772. So this one is 15. This one is 16. And then we don't actually have to plot these points. She has already plotted them for us. She plotted the probabilities associated with each of these outcomes. So one of them is, you can see, everyone look at the graph real quick. The leftmost point, the 198, had associated with it what probability? 0.0062. And as you can see, it's very, very close to 0, right? 200 was the very first one we calculated. I believe that was like 0.066 something, 0.0662. That was question number 3, or no, question number 2, right? And then the next point on the, as we start to peak up a little bit higher, that would be for 205. We did that in part 3. That was found to be 0.841. No, that was probably part 4. Yeah, probably that was question 4. And that probability was 0.84 something something. And then the last one we just computed in question number 16. Question number 16 was the 0.9772. So all those points are plotted to form what is called the probability rejection curve or something like that.
So when I did normal CDF for -1,000, -2.
Why did you do why did you do -1,000, -2?
It's 1,000.
Is it just 1,000?
Well, wait. Why did you do? Wait, you're just assuming that. Okay, you did -1,000, -2. Why?
I don't know. I just did it.
But
like,
this is, we're always trying to do what here? The question is, what's the probability of doing what?
rejecting.
So we want a left tail value or a right tail value?
Right tail.
Yeah, but this is a what? If you do normal CDF of -1,000 to -2, which tail are you getting?
That's a left tail.
Yeah, you're saying -2, and I want everything to the left of that -2 value, right?
Yeah.
Now, your instinct for that was because, well, we did this in problem 3, I think, right?
Hmm.
What did problem 3 say? Scroll up and read problem 3. Problem 3 says, what's the probability of doing what? Or calculate the probability of
Type 2 error.
a type 2 error isn't rejecting, it's doing what?
Accepting.
Accepting. So the question, so that's what we did the left tail for number 3. We did a left tail for number 3 because they wanted a type 2 error, and a type 2 error isn't rejecting, it's, as you said, it's accepting, right? So your brain automatically thought, oh, okay, I got a negative z-score, so I need to do what I did in question 3, which was do -1,000 to the negative value. But in question 16, I'm not trying to find the probability of acceptance. I'm trying to find the probability of what?
Rejecting.
Which is the right tail, right? So don't just assume that because I got a negative value, I need some sort of left tail. This time it's still a right tail, but because I'm being asked to reject.
Okay, so then I would do the lower is
Negative.
1,000, the uppers.
Nope. What's the lower bound? So again,
-2, and then the upper is 1,000.
just say this. Here's my z-score, -2. Which tail do I want? Do I want this side? Or do I want this side?
I get it now.
So my lower bound is -2 there, and I want 1,000 my upper bound. Okay. Continuing to number C. So let's actually clear all this mess. We don't need this anymore. The rejection probability curve. So for a right-tailed test, the rejection probability curve looks like this. And then, as you can probably guess, for a left-tailed test, looks like this. And then for a two-tailed test, the curve looks like this. Okay? So take a mental snapshot of that if you'd like, but this for a right-tailed test, the rejection probability curve looks like this guy on the left, which we're going to do. So I'm going to erase all this stuff because our test is right-tailed. So we'll be doing our rejection probability curve looks like that. It already does. She displayed it to us, and my job is to tell you what each of these things are. So first things first is the magical value that we mark down in the middle is the null hypothesis value, or it's like the H null value, which was 200, right? I've got 4 different things labeled. One of them, there's this guy. There's this guy. Let's do 2 more. There's this guy. And there's this guy. Got some orange and blue, my alma mater. Go Gators. Let's put a pink lid on this. This is 1. Okay. So this guy is correct rejection, aka power. This guy is alpha, or type 1 error. I gotta put this somewhere else. Let's draw an arrow to him. This guy is correct acceptance. Doesn't have a name for that. We call correct rejection power. We don't have a name for correct acceptance. And then this guy, the only thing, what's the last thing we're missing? Who are we missing? We've got correct acceptance, correct rejection. We've got incorrect acceptance.
Sure.
I screwed this one up. This is not, wait, yeah, we're good. This is type 2 error. Incorrect rejection. This is incorrect acceptance. So type 2 error. Incorrect rejection. Nope. Incorrect acceptance. And this guy would be incorrect rejection. Okay, that helps you then answer 17, 18, 19, and 20. 17, curve C is, according to mine, correct rejection, aka power. Segment D, this is 18, segment D is type 2 error. It's incorrectly rejecting, or incorrectly accepting the null, which would be D, type 2 error. What is segment B? Segment B is type 1 error, incorrect rejection, and then line segment A is correct acceptance of the null. Okay. 21 through 26 are our last problems. Do we have anything else? Hold on a second. Give me one moment. There's a knock at the door, so I want to address that real quick. Be right back. Okay, guys, I'm back. Sorry, I hope you didn't miss me too much. I'm going to clear all this. And we will tackle 21. The miniature wants to control the maximum probability of type 1 error at 1%. This is now reverting back to a question where you guys know already how to do this based on my cheat sheet. So this is find the critical value. So this is do the rejection region method that we are already familiar with. And this is the one mean. Do the one mean rejection region method we're already familiar with. If you do not already have the one mean cheat sheet, you can ask me after this is over. Once I stop the recording, you can say, hey, Andy, I don't have that. But you should have it. I shared this in the group me, so you should have the one mean section out. You're going to follow the steps that are associated with the rejection region for one mean. So step 1 says ascertain whether this is Z or T. I believe we already established that this is a Z distribution. This is still a approximately normal distribution with a known population standard deviation of 18. So we're going to use the Z distribution. Step 2 says, what is step 2? Oh, get your value of Z. So in our case, Z would be inverse norm of. What does my cheat sheet say? Well, it depends on whether this is a left, right, or two-tailed test. So what tail test we say this was? Left tail or right tail or two-tailed? What tail test was this? This is still the same question, so we should have the same answer from before. The null hypothesis is that mu is less than or equal to 200 versus alternate.
Right-tailed?
It is indeed a right-tailed test. So because it's the right-tailed test, Evelyn, do you have my cheat sheet? The one mean, it basically says one mean at the top. Do you have that?
Yeah, I think so.
Okay, and then I think for the one mean, so you should, do you have it in front of you? Because if you don't, it's no big deal. I'll just kind of.
Yeah, I do.
Okay, so looking at step 2, I need to get my z-score, and that depends on what tail test it is. So for a right tail test, it requires what? Inverse norm of what? Alpha over 2 or 1 minus alpha over 2?
1 minus alpha.
Oh, just 1 minus alpha. Okay, so 1 minus alpha. In our case, what level of significance did they ask us to use?
0.01 or 1%.
Yep, 1% or 0.01. Good. So we're going to do inverse norm of 0.99. That's going to give me inverse norm 0.99, 2.326. That is my z-score. Now step 3 is then going to tell us to move on and find the critical value. And the way we find the critical value is solve for the critical value in the formula z equals CV minus the H null value over standard deviation over square root of n. Well, we know basically all these numbers except CV. We know that z is 2.326. We don't know CV. After all, that's the thing we're solving for. The H null value is 200. The sigma is 18, and our sample size is 81. So we're going to solve for CV. When you solve for CV, you get 2.326 times 2 plus 200. I get CV equals 204.652. That is your answer to, I think that's what they want, right? They want the critical value. Calculate the critical value. Yep. So this is question number 21. 22. Using the critical value we calculated in the previous question, what is the probability of a type 2 error if the population mean is 205? So this is tricky. We'll say, what's probably a type 2 error? Again, that's the probability of accepting the null, even though HA was true, aka probability of being inside or being outside RR, given HA is true. And what alternate hypothesis value do they want us to use? Probability of X bar being less than 204.652, given mu is what value? What value of mu do they ask us to use? What population mean what does the population mean now? It was 200 before, but now it's what? For question 22, they want us to assume the population mean is
205.
205. What do I always want you to do anytime you're given a probability statement about a normal distribution? Your job is to convert all the X bar stuff into
Z-score.
Z-score. So let's do that with that handy dandy Z-score formula. Let's do that in orange. Nope, let's keep this as green and let's do this in orange. We will say Z, give me orange. Z equals 204.652 minus 205 divided by 18 over square root of 81, which comes out to be negative 0.174. So we have, what's the probability that Z is less than negative 0.174? That means I'm going to do normal CDF, negative 1,000, comma, or negative 100, doesn't really matter, comma, that Z-score we got, negative 0.174. Why am I doing less than? Why am I doing this less than this time? Brendan, am I trying to reject or accept this time?
I was just gonna say you're trying to accept, so that's why you're doing the less than, because you want to be the left tail.
Exactly. We're doing a left tail here because we wanted to accept rather than reject. So normal CDF, negative 100, comma, negative 0.174. This gives me 0.4309. Okay, and that's your answer to 22. We've got a few more left. 23. If the sample mean turns out to be 205, what is the conclusion of the test? So this is where we continue on with step 4 of my cheat sheet. Step 4 says create your rejection region. So this is 23 is go on to step 4. Rejection region equals X bar bigger than CV, and that CV we found back in question 21 was 204.652. Step 5 asks us if we were to check what X bar is, or we were given X bar equals 205, what's the conclusion of our test? Well, question, is 205 inside our rejection region or not? Does it satisfy one of the equalities in our rejection region? Yes, it does. We would say something like, because X bar equals 205 satisfies the inequality in our rejection region, then we reject the null hypothesis. So that's our answer to 23. We're going to reject H null in favor of HA. Continued, calculate the p-value. Okay, p-value is a little bit complicated. Not too complicated. Let's do that. So p-value. I don't know if the steps for p-value are on the cheat sheet I have, or at least the version that some of you have. So with that in mind, I will show you how to do p-value. P-value steps are as follows. Step 1 is get a z-score, where you're going to be given X bar, mu, p-value if what? Okay, sample mean is 205. Mu from H null, standard deviation, and sample size. Step 1 is to find the z-score. Well, we know how to find a z-score for given X bar, so that would be 205 minus 200 over 18 over square root of 81. This number will look very familiar, by the way. We get 5 over 2, which is 2.5. Step 2 is, if left-tailed, do normal CDF of negative 100 comma z. If right-tailed, normal CDF z comma 100. And then if two-tailed, do both of these. And then your answer is double whichever is smallest or is smaller. Now, in our case, we don't have a two-tailed test. We don't have to do both of these. We merely have to do this one because our test is right-tailed. So as our test is right-tailed, we only have to do normal CDF 2.5 comma 100. We've already done this, though. We've already found 2.5 comma 100. This was 0.0062. Whoops. Did I just lose it for good? Great. Well, that one's gone. 0.0062. That is your answer to 24. We have 25 and 26 as the last two. 25, which of the following describes the criterion for rejecting the null hypothesis using the p-value approach? Here's the phrase. You say, if the p is low, reject the ho. What that means is, if the p-value is lower than the significance level, then reject the null hypothesis. Again, the crass way to say it is, if the p is low, reject the ho. But formally, this is, if the p-value is lower than the significance level, again, the significance level is alpha, aka lower than alpha, then reject the null hypothesis. So that would be answer choice B, reject H null if the p-value is smaller than the significance level. Look at your answer to question 22, which was what? It was like 0.17 something, or no, 0.4 something, I forget. The manager decides the probability, I hate this question. This is the minimum sample size question. I hate this one. Okay. There is a formula. Oh wait, one second. Someone's got to chat. 0.403.39. Good, thank you. Turns out we didn't need that, but thanks for being helpful. So this is. Let's do bold here. Minimum sample size needed to control both alpha and beta. Here's the formula. Z alpha plus Z beta. I don't even remember my formula. Give me a sec, guys. I gotta find it. Downloads. I'm gonna share you on this real quick. This is the document that you get when you sign up for the final exam review, or if you sign up for any of the practice sessions. This is old. This is really old, right? I don't think you have access to these exams, but you have access to these. We are going to scroll down to the section that corresponds to minimum sample size. Minimum sample size needed to control alpha and beta to a certain value. So this is the magical formula here. I'm going to write this out on the whiteboard. But we have to do a couple things. We do either inverse norm of alpha and inverse norm of 1 minus beta as our z alpha and z beta, or we do this one, and this one of our tests is right tail. Now, as a reminder, what tail test was ours? Was our a left tail test or a right tail test? You guys keep forgetting. It's really important that you probably write that on the top of the. Did I mute you? I didn't give you a chance to unmute yourself, maybe.
Right.
Okay. It's a right tail test, right? I share it. The PDF gets shared with anybody who signs up for the final exam review or any of the practice reviews, the practice exam review sessions, final exam sessions. Again, final exam or the final exam practice sessions, but of which I'm doing 3. Okay. We're going to follow this formula here. We do inverse norm of 1 minus alpha. Going back to the whiteboard. And z beta is just inverse norm of beta. What did they specify for alpha? What did they specify our value of alpha was?
.01, right?
0.01, I believe. Yeah, let's see what the question says. I didn't actually read it. Yep, the manager wants the significance level to be 1%. So this is going to be 0.01. And what do they want the maximum probability of a type 2 error to be? What is 0.1? Good. So 0.1 versus 0.01. So I want you guys to plug these both into inverse norm. Let's see. Sigma was 18. What did someone get for Z alpha? Is that 2.32 something?
Yeah, 2.3263.
Okay. And then what do we get for Z beta?
Negative 1.2816.
So I'm going to make a mistake here deliberately. We'll see if you guys catch it. Mu null, this would be 200. And they said, what should I assume about the alternate hypothesis? I want the type 2 error to be at most 10% in the event that the alternate value of mu is what? They have to specify some sort of alternate value of mu, otherwise they can't do this problem. So did they specify some alternate value of mu? This was the null hypothesis value. Someone must have typed it in chat. Let me see what they said. Yes, Tyler's right. They specify in the event that the alternate value of mu is 205. So stated in the question. So we'll say mu sub HA. And this will be mu sub null hypothesis. This is not yet right. What mistake did I make in this formula?
Should it be plus 1.2816?
It should. Yes, because Z beta was negative 1.28. So this is minus negative 1.2816. And as a result, that makes that positive. If we do this, punch this all in, 18 times 2.3263 plus 1.2816 divided by 5 squared. Why doesn't it matter? Oh, some people say, Andy, divided by 5, but technically I should be divided by what value?
-5.
Why doesn't it make a difference?
It's squared.
Yeah, so it wouldn't matter if I divide by 5 or -5. When I square the result after dividing by 5, I get 168.69 or 1.68.7. Of course, what do we always do in these sort of situations?
Round up.
Round up. So this is going to be a 169 as our answer. I want to point out that I think on this particular quiz, you were not asked to find the critical value, but I think last semester she did ask you to find the critical value. So how could I have done that? Well, there are formulas right next to the formula I told you to look at to do this problem. Is this the one? No, this is the one. You could use either this one or this one. That I have the null hypothesis value of 200. I know this is 18. I know this is square root of 81. I know Z alpha to be the 2.36326 I just used. So I just, oh, and by the way, what n do I use now? I use, instead of n equals 168.67 or 69 or whatever, I'm supposed to use 169. Okay. Not that you were asked for that, but in case you needed to. Okay, has anyone been following along and plugging all these answers into the quiz? All right, well, guess we'll find out later on whether or not we're right. I don't even think don't have time to get to quiz 16. I'll do a little bit of it. Maybe what I'll do is one second. Let me see what quiz.
I have a question.
Yeah, sure.
What did you guys put for 8? Because I have written down type 1, but on question 8, I don't see type 1 as an answer.
What is 8?
Level of significance.
I have type 1 written down.
Yeah, but type 1 is better known as, so
Significance level
yes.
or alpha?
Yep, so this is a reminder. Type 1 error is better known as alpha, is better known as significance level.
Okay, thank you.
Mm-hmm. These are all synonymous with each other. Okay, this is enough for today.